I want more for the same money. So if for $2 I could get a beer of this size, wouldn't it be attractive if instead for the same $2 I could get a beer of this size? It has to be a better thing. In this project we're really targeting logic density, and we're going to actually look at the core of the FPGA itself to try to cram more computation into a given area of silicon. So logic density, kind of defining as implement more gates per unit area of silicon. I'm going to skip this for this audience, but ASP-DAC will be a more general audience, so I have a bit of introduction into lookup tables for that audience. So today's FPGAs, we know that the modern FPGAs use 6 input lookup tables. And the reason for that, going to 6 input versus 4 input, is you use fewer levels of lookup tables, which means you have naturally fewer levels of interconnect between the lookup tables, and that will give you better speed. However, many logic functions use less than 6 inputs, and it's hard to efficiently utilize 6 input LUTs. So in the commercial vendors, what they've done is that they've taken the 6 LUTs in modern chips are fracturable to improve logic density. And that really allows you to take 2 small LUTs, cram it together into one 6 input LUT. I'll tell what fracturable is in a moment, but just to remind everyone, what is a 6 input lookup table? It has 64 SRAM cells, has basically a decoding tree with 63 2-to-1 multiplexers in that tree. Within a 6 LUT, you have here 2 5 LUTs, and one of the inputs is really selecting between those 2 5 LUTs, and the other inputs are the inputs to the 5 LUTs. They're shared between those 5 LUTs. In commercial chips, in the Xilinx style and Vertex 6, the 6 LUT has 2 outputs, and basically that's done by tapping off these 2 5 LUTs. You can tap off and make those separate outputs in essence. So you can have one 6 input function or any 2 functions that use up to 5 inputs. In the Altera style, it's a more flexible adaptive logic module. This structure here has 8 inputs, 2 outputs. It can have one 6 input function, 2 4 input functions, or a bunch of different combinations, a 5 and a 3, etc. So you have 8 inputs coming into that structure. So basically these dual output LUTs are one way of improving logic density and getting good logic utilization for 6 LUTs. In this article we propose a different way of getting logic utilization, improved logic utilization. And basically it uses this concept of Shannon decomposition. We've all learned about it in 2nd year. In fact, I forgot about it, but last year I was assigned to teach 241, so I relearned Shannon decomposition, what it was, and then it actually inspired this work of that because I was teaching the Shannon decomposition. But just to remind everyone, if you have a logic function here, say it has n variables, you can take one of the variables, say xi, and you can decompose a logic function with respect to that xi. So you take a chunk of the logic function where xi is assigned to 1, and you have another basically part of the logic function where xi is assigned to 0, and you use xi to basically select between these 2 pieces. And this first part right here, where xi is given a value of logic 1, that is called the 1 cofactor. And that can be denoted by g sub xi. And the second chunk right here, where xi is given a value 0, that's called the 0 cofactor. G sub xi bar is the notation for that. So there's a 1 cofactor and a 0 cofactor. Cofactor properties, we actually in the article, we use this notation to represent the number of variables in a cofactor. Okay, we actually called it the size of the cofactor. Now if I have an n variable function and I do Shannon decomposition with respect to one of the variables, then the cofactors for sure have to have n minus 1 or less variables, okay, because basically I've taken one variable out in that case. We also define something called a trimming input. We couldn't find another name for this in the existing literature, but we defined this notion of a trimming input, which is that, say I have a k variable logic function right here. We say it has a trimming input, xi, if Shannon decomposition with respect to xi produces a small cofactor that has less than k minus 1 variables. So for sure the cofactors are going to have less than or equal to k minus 1 variables. But it could be they actually have less than k minus 1 variables. And if they do, we say that input, when we do the Shannon decomposition with respect to it, we trimmed away extra variables. So we called it trimming input. We couldn't find another name for that, but it's we're calling it trimming input. Example, 4-variable function right here, a and c, or a naught and b naught and d naught, or d naught and a. If we take Shannon decomposition with respect to d, if we look at the 1 cofactor, we get a and c, or a naught and b naught, has 3 variables. But take a look at the 0 cofactor. A and C, or A, which is just A, which has only one variable, so we would call D is a trimming input because this 0 cofactor has less than 3 variables, so we call that 0 cofactor. Okay, so why does this trimming input concept, what does it give you? Well, first of all, how common are trimming inputs? How common are these trimming inputs? We actually analyze that. On the horizontal here, you see the names of 5 circuits. And on the vertical, what we did is we mapped those circuits into 6 LUTs, and we just looked at the 6 LUTs, and we checked of all the 6 LUTs, how many of the 6 LUTs have at least one input. It is a trimming input. Okay? And actually, these trimming inputs were extremely common, especially in the MC-NC circuits, and we found it's maybe less so in other circuits. I'll show that in the results. But the trimming inputs were actually very common. So more than 90% of 6 LUTs in mappings had trimming input. They're extremely common. So the nice thing about trimming input is that if a 6-input function has a trimming input, you don't need full computational power with 6 LUT to implement that logic function. It actually can be implemented in this structure right here, whereas basically you put the trimming input, you attach it to input I6 right here, and remember, one of the cofactors will be small. That can go into this 4 LUT, and the other cofactor, potentially big, could go into the 5 LUT right there. And this we're calling 5 plus 4 LUT architecture. Still has 6 inputs, but it actually uses less SRAM cells than a 6 LUT. This would have 49 SRAM cells and fewer versus 64 in a 6 LUT. The reason we put this optional inversion right here is we don't know whether it's the 0 cofactor or the 1 cofactor that's going to be the small one. And we actually analyzed it. There doesn't seem to be any obvious tilting on that. So in this case, since we have optional inversion, either the 0 cofactor or 1 cofactor could be the one that is the small cofactor. So this is 5 plus 4 LUT architecture. A special case of trimming input is something called gating input, which is a word that is used in literature. Gating input is a special case of trimming input where basically one of the cofactors has 0 variables. There's an input to the function where one of the cofactors has 0 variables. Interpretation, that means there's one input to the function that when that input is in a particular logic state, logic 0 or logic 1, the function just immediately goes to a known state of 0 or 1. It's like an AND gate, for example. If any input is 0, the function is 0 in an AND gate. Okay? Example, 4 variables, A and B, A or B or C in brackets, and D. If we do the Shannon decomposition with respect to D, the 1 cofactor has 3 variables. The 0 cofactor is just logic 0, has 0 variables. How common are gating inputs? Gating inputs are not as common as trimming inputs because it's a special case really of trimming inputs. But they are still significant. There still are quite a few, so it's in the range of, the MC-NC circuits have more gating inputs, other circuits have fewer, but there still are lots of gating inputs. Gating, if my logic function has a gating input, 6-input logic function has a gating input, it can fit into something even smaller, this structure right here, which we call extended 5 LUT. This is kind of a generalization of something we did in FPL 2009. But any 5-input function can fit in here, as well as any 6-input function if I attach the gating input to there, right, I6. And the gating state can be, if it pulls it to logic 0 or logic 1 in the gating state, I can put that in that SRAM cell right there. This has very few SRAM cells, only 34 SRAM cells. We call this extended 5 LUT architecture. So if you can find trimming inputs and gating inputs easily, then you can consider all kinds of different architectures actually quite easily. Okay, so we actually consider a bunch of different architectures. One of them, shown right here, we called it 2 extended 4 LUTs. And what you can see is here we have a 4 LUT, extended 4 LUT, and another 4 LUT, and then we have a mux between them at the end. All these are 6-input architectures. Okay? Taking a look at this guy right here, we can implement for sure any 4-input function because we have a 4 LUT, any 5-input function because we have this muxing here between these two 4 LUTs, as well as some 6-input functions. As long as if I do a Shannon decomposition with respect to some variable, it gives me 2 cofactors that either of size 4 or that they have gating input. Okay? We call this 2 extended 4 LUTs. Another version of that is you take one of these 4 LUTs, make it a 3 LUT. We call that extended 4 LUT plus extended 3 LUT. That has even fewer SRAM cells, less than half of a 6 LUT. We're now getting very small. And another one right here, we called it extended 4 plus 3 LUT, which basically has a 4 LUT, 3 LUT, and a 3 LUT, muxing to select between the two, and then a gating input concept right here. Turns out it's actually very easy to map into these. Although the architectures look maybe complicated, it's actually quite easy to map into them with ABC. And in fact, you know, there's been a lot of work previously on trying to combine LUTs with muxes, but historically it's hard to do a broad exploration because it's kind of hard to map into them. But if you have this ABC, it turns out it's very easy to find the gating inputs and trimming inputs. ABC, just to remind everyone, it's a logic synthesis system developed UC Berkeley by Mischenko, mainly. Main data structure in ABC is an inverter graph. Basically, the logic circuit here can be represented as a network of 2 input ANDs and inverters. The inverters are not explicit. The inverters are just tags on edges. So basically here I show inversion with a dotted edge. Okay? This is the idea of ABC. Now, despite this simple data structure, in logic synthesis today, all the highest quality LUT mapping results and even logic synthesis results are actually coming out of this ABC, despite the simplicity of this data structure. Okay, so you actually get very good mapping solutions when your input netlist is represented by the simple AND inverter graph. So I said it's easy to find these Shannon cofactors with ABC. Why is that the case? Let's say I have this AND inverter graph. I want to find 0 cofactor with respect to B. It's easy because your only gates are AND gates. That's why it actually makes it very easy. So say I want to find the 0 cofactor with respect to B. I attach a logic 0 to B. Now, since it's an AND gate, if one of its inputs are 0, its output has to be 0. So bang, that one's out. Its output is 0. Now, since its output is 0 and it's feeding into this other AND gate right here, that one is also eliminated, basically. Okay? Now, since this one's output is also 0, but it's feeding into an inverted edge, that makes a logic 1 input to this AND gate right there. Okay? So in other words, setting an AIG input to a logic 0, logic 1 basically eliminates some portion of the AIG. It just chops it. Chops it out, basically. So in this case, I end up with a logic 0 right here, and this chunk right here is kind of just gone, and I'm left with this chunk right here, and this reduced logic function right there. So it's actually very easy to find these Shannon cofactors in ABC. It's very easy. So how do we map? We got all these architectures with different LUTs and multiplexers arranged in weird ways. How do we map into them? Well, we did that using this mapper in ABC. We hacked it to map into these architectures. And all the good mapping solutions for FPGAs now are based on this notion of cuts. And the idea with the cut is that basically if I have this graph, I'm trying to map it into, let's say, 3 input lookup tables. And I want to find the different 3 LUT mappings for node Z right there. I cut Z's predecessor network. And as long as there's no more than 3 edges crossing the cut, that's a legal mapping for Z. So here's 3 possible cuts for node Z. And you can see that they each have no more than 3 edges crossing the cut. So those are 3 possible LUT mappings for Z and some of its predecessors. So there's a lot of detail here I'm just skipping over. This is the rough idea of FPGA tech map. You can use this idea of cuts. And the basic details is you walk the circuit from primary inputs to primary outputs. As you come to a node, you find all of its possible cuts. You cost the cuts, you select the best cut for each node, and then you walk the network in the reverse direction and you start instantiating LUTs based on those best cuts. Okay? The way we map into all these different architectures is we change the cut-based mapper, so we just ignore cuts that can't fit into the architecture that we're trying to map to. So we just skip over those ones. They're disqualified, basically. So we discard cuts that don't meet the target architecture, and that's easy to check with this AIGs and inverter graphs in ABC and Shannon decomposition. So for example, if we're mapping into this 5+4 LUT architecture, say we have a cut C in tech mapping. If that cut has only 5 inputs, it's qualified. No problem. If it has 6 inputs, we have to walk through its inputs and see if one of them is a trimming input. If we can't find trimming input, that cut is eliminated for this case. Likewise, another example, in this case a little more complicated, any function that uses less than or equal to 4 inputs, that's fine here because we have a 4 LUT. Any function that uses 5 inputs, we're looking good because we have 2 4 LUTs and we can use this mux here to select between them. For 6 input functions, a bit more messy. Basically, if we can find an input to a 6 input function where both cofactors have 4 variables, that's fine. Or both the cofactors have to have a gating input, and that gating input would be attached to I5. So basically, a rough idea, all the details are in the article, but by just eliminating and disqualifying some cuts, we can actually map into a wide range of architectures. For methodology experiments, we looked at two metrics: number of logic elements needed to map circuits, as well as the mapped circuit depth, the number of logic elements on the critical path, which is proxy for speed. We use the usual MCNC20 circuits, but we also use the 13 VPR5 circuits. For those VPR5 circuits, we needed to get them into BLIF because we need to push them to ABC, so we synthesized them with Quartus and used QUIP to dump BLIF after the technology independent optimization. So for these VPR5 circuits, they were kind of logic is pre-synthesized with Altera with technology independent optimization. Baseline mapper, we use the priority cuts mapper in ABC. Okay, that's a cut-based technology mapper. It's already in ABC. We use a standard script for technology independent synthesis. Each circuit we actually mapped, we did tech independent synthesis and mapping 6 times for each circuit, and we chose the best result of the 6 times. We actually borrowed this methodology from Mischenko. He's doing that in his papers too. Okay. Results. Okay, basically here you see the different architectures on the horizontal. On the vertical you see geometric mean ratio of depth. Maroon bars are depth, yellow bars are the number of logic elements you need to implement circuits. Everything's normalized to 6 LUTs. Everything's normalized to 6 LUTs. With 5 LUTs you can see with depth you need about 14% more levels of LUTs with 5 LUTs versus 6 LUTs. And you need about, say, again, 14% more logic elements to implement circuits. So, you can see depth-wise, that's the reason people have gone to 6 LUTs. It's well motivated. Now, the VPR5 circuits are actually deeper than what I've done here is that I've actually added error bars onto each of these bars, which are going to show the difference between the VPR5 circuits and the MCNC circuits. The reason I did it because we see actually considerably different results for the VPR5 circuits versus the MCNC circuits. So I'm using this error bars in Excel to demonstrate it. The VPR5 circuits are actually deeper than the MCNC circuits. The hit for 5 LUTs depth is higher for the VPR5 circuits. However, they consume a little bit less area than the MCNC circuits relative to 6 LUTs. Now let's take a look at the new architectures that we basically proposed in this paper. 5+4 LUT architecture, if you recall, it looked like that. As you can see, on the average depth, the number of LEs, because those trimming inputs are extremely common, you almost get identical depth to 6 LUTs, and you have a very similar number of logic elements, even though you use a lot less SRAM cells. That's because those trimming inputs were actually quite common. The VPR5 circuits were a little bit worse from the depth and logic elements perspective. You can't actually see the bottom of the bars, which is the MCNC circuits. It was virtually identical to 6 LUTs for the MCNC circuits. The VPR5 circuits were a little bit worse. Again, the VPR5 circuits were pre-synthesized with Altera Quartus 9.1. So 5+4, you get nearly identical depth number of LEs to 6 LUTs. What about extended 5 LUT? Looks like that. You use about 5 to 6% more depth and around 7% more logic elements. But this is actually much smaller than a 6 LUT. It has only 34 SRAM cells. Okay? And again, the top bars are for the VPR5 circuits. Somehow they did not contain as many trimming inputs or gating inputs for the VPR5 circuits versus the MCNC20. This other architecture, we called it, if you call it 2 extended 4 LUTs, it's actually better than that extended 5 LUT that I just showed. It has about 5% more depth, and it has about 6 or 7% more logic elements needed to implement circuits. But this is actually very small compared to a 6 LUT. It actually has only 35 SRAM cells versus 64 SRAM cells. This is pretty good architecture. So it's better than extended 5 LUT for about the same area. Now the really small architectures, 4 plus 3, extended 4 LUT plus extended 3 LUT, shown right here. Basically, you can see here the area, number of LEs, is actually quite a bit bigger than 6 LUTs now. It's about 12% bigger. Depth is still only about 6 or 7% bigger than 6 LUTs, and this is pretty small architecture. But what we saw is that the difference between the VPR5 circuits and the MCNC circuits was actually getting very pronounced for these small architectures. They're not as easy to map to for whatever reason for the VPR5 circuits. And we got similar results for the other very small architecture, which we called extended 4+3 LUT, shown right here. So these two sets of results are very similar. We tried to make a rough back-of-the-envelope calculation of, so far I've been talking about number of logic elements and depth. I haven't said anything about silicon area, okay, and actual logic density in silicon. We tried to make a back-of-the-envelope calculation of logic density in silicon, and again, this is back of the envelope. I may face a lot of bullets afterwards for this result, but that's fine. So if you assume that in a 6 LUT based FPGA, say the LUT is 25% of a tile and interconnect is 50% of a tile, and flip-flops carry and other circuitry is 25% of a tile. Basically, all these architectures use 6 inputs. They could be directly embedded into an existing 6 LUT fabric without any changes to the routing. We assume that only this LUT area would be reduced by these proposed logic element architectures. How much would it be reduced? We assume it would be reduced in proportion to the number of SRAM cells in the LUT, okay, which is also similar to the number of 2-to-1 multiplexers in the LUT. So a 6 LUT has 64 SRAM cells. We can compute the ratio in number of SRAM cells for each of these different architectures. Okay? Then we can try to estimate the overall improvement or change in logic density in the following. Just the 25% term is affected by the area reduction of the logic element. Okay, so these ratios right here I'm going to be plugging in as these S values right here. However, for all these different logic element architectures, you need more of them to implement circuits. So we have to account for that, and we account for that through this F term, which is going to be greater than 1, which is the ratio of the number of LEs needed for circuits versus 6 LUT. So it's a kind of a crude way to estimate the improvement in logic density. If you do that, you get this chart right here, which has, again, maroon and yellow bars. Maroon bars are the silicon area relative to 6 LUTs. Yellow bars are silicon area times depth. So we try to do area depth product for yellow bars. As you can see, this 5+4 LUT gave us our best result in area depth product. That requires just 6 input functions, have 1 trimming input. That got about 5% better in area depth product. Some of these small architectures, extended 4+3 LUT, actually had much better silicon area. It's about 14% better silicon area than 6 LUT. So these architectures really offer a new way of improving logic density, and you can choose different points depending on whether you're targeted on area or area depth product. So in summary, we found that logic functions very often have trimming inputs, and gating inputs are somewhat common. These kind of inspired new logic element architectures for us, and these architectures can get an improvement in area depth product and also in the logic density, basically silicon area. In the paper, we also put results for 7 input logic elements, because if the trend continues, you might eventually see 7 input logic elements, so we thought we could discuss that also in the paper. Future work, we actually, these ideas, they all contain multiple LUTs inside, so they're not incompatible with fracturable concept. You could still do fracturable concept with even these other architectures. Dual output 5+4 LUT, this is certainly conceivable. So you could try to combine this technique with fracturable technique. Maybe that will give you even more logic density. Likewise, there's been a lot of work in logic synthesis on don't cares. So you could try to use don't cares also when you map to these, and maybe you will get even improved results from that. So that's the end of the talk. Any questions? Jason.
So with your new logic element style, you're going to lose logical equivalence for the select lines of those head-top multiplexers. Do you think that this will have this will impact the routing area, or do you think this is going to have like a negative impact?
It could impact the routing area. It's a very good point, and it also could. Often you put the most critical pin on the deepest input in a 6 LUT. So in this case, you couldn't do that. You'd have to put the trimming input first, for example, on the deepest input of the LUT. But on the other hand, if your tiles are smaller, then your wires and capacitance will also be shorter. So you may get some delay improvement from that. So it's not necessarily that you would actually lose performance. You might get actually flat performance because your tiles will be smaller. So even with the 5+4, we're seeing very similar depth, but it would have smaller tiles, so it should have shorter wires and better delay than 6 LUT. But you're right, I mean, it's a very good point, yes, and it's again, we would like to investigate that. It's kind of hard to investigate, but yeah, whether basically when you lock a signal to a pin, do you lose routability? How much do you lose, right? And basically, does it cost you in routability angle? Greg?
So I guess a power question. So when you're doing mapping, do you think your choice of cofactor bit would have a significant impact on dynamic power?
Okay, in what sense, I guess?
Well,
yeah.
so the cofactor bit is choosing one part of the circuit or the other. So if you chose a bit that happens to switch a lot versus one that doesn't, it seems like that might have more or less of an impact on dynamic power.
So yeah, so basically when you're choosing one, you have to take one signal, let's say has a trimming input, and put it to a particular input to your logic element, right? And now you still had to, even in a standard 6 LUT architecture, you still had to route that signal to the logic element here, but you might be locked to a specific pin. Now, if getting to that pin cost you more routing area, kind of like what Jason was asking, if you had to take a roundabout path in the routing to get to that pin, then indeed, if that was a very toggly input, then yeah, that would hurt you for power. But it's not exactly, power impact is unclear. You should have smaller tiles, shorter wire lengths, less capacitance, which should help power.
Right. That's
So,
that's the static side.
yeah. So in other words, I can't give a clear, I can't give a for sure answer to your question. I don't know. Yeah.
Okay.
It's a good question. Brayden.
All right, question from the chat room is, what's the runtime hit of the cut pruning step?
We didn't even measure it. It's almost the same runtime as without the cut pruning. So it's very fast to find these trimming inputs. You're doing a fast traversal of the end inverter graph, and then you're basically marking some AND gates as out of it, and then what you have left, you see how many input variables you have left in it. So it's not significant, the runtime hit. Jonathan.
Where did you get your 25% number on? It's kind of the key number that gets you your area gains. Where did that come from?
Anecdotal.
It strikes me as a teeny bit big. But,
For 25% for the LUT. So
for the LUT RAM, I don't know if anyone.
It's not just the LUT RAM. Also, the size of the multiplexer is also reduced, right? So it's the whole LUT, and the size of the multiplexer is reduced in proportion to the same proportion as the number of SRAM cells.
These are the multiplexers inside the LUTs, but not the multiplexers inside the block itself that are doing the internal routing.
No, and we assumed that was in the 50% of the tile. That 50% of the tile was routing. So that part is a constant. We're only attacking the 25%. If any industrial people want to say what fraction of a tile is LUTs, we're happy to hear it.
I don't know off the top of my head, but the 25% doesn't strike me as out of line. I think that's probably close to what my guess would be as well.
Okay.
I don't know if my guess would be right or not, but it strikes me as out of line. Could you run through VPR 5.0 to measure the impact of the fact that your LUTs are less rotatable now? Basically just make fewer logically equivalent pins and just model it.
We could do that, yes. So we would have to figure out a way to basically, yeah, so VPR 5, where, if you target a cluster-based architecture, then assume the full crossbar, right, within the cluster. Right? So basically when you hit the logic block, once you hit the logic block, it was a full crossbar to hit any LUT input inside there. So you'd have to somehow, wouldn't you have to have routing up to the LUT pins, LUT input pins or something to properly investigate that?
It's probably two separate questions. There's nowadays most clusters are depopulated, so really you should model that.
Sure,
But
sure.
let's say you just ignore that,
Yeah.
because that's arguably a separate question.
Yeah.
You need a different delay for every LUT input, which I didn't participate in the 5.0 upgrades, but the older version of VPR could do that in the timing graph,
Yeah,
just not in the architecture description.
right.
Once you upgrade that timing, you at least get the LUT impact. You would probably still have a somewhat optimistic answer, you're right, because you're modeling a little more routing flexibility than people commercially build nowadays.
Yeah.
But you can just say it is what it is, you model this, and you put that answer.
Sure.
Probably partially show you the answer.
Yeah.
They show
Yeah.
the impact of not being able to get the fastest path through the LUT.
Yeah, I mean, absolutely, that will give, it's a nice piece of future work. It seems like a ton of modeling to make that work though, and even maybe some algorithm change in APR, but.
Yeah, it's a lot of work for somebody, I agree.
Yeah.
One of the comments, I think the fracturable LUT future work is interesting and pretty important, because I suspect you're gonna find fractional LUTs are intended to capture some of that unused circuitry, right?
Sure,
Like
sure,
there's a
sure.
big mux tree and all these SRAM cells, and you know that a lot of the time you don't find a big enough LUT, and therefore you won't use them.
Yeah,
You're also capturing some of that unused circuitry.
well, I'm actually reducing it, actually.
Yeah, you're removing the unused
Indeed,
circuitry
yes,
instead.
indeed.
And you could combine the two concepts, but the answer is not obvious of what happens when you compete against a fracturable LUT, since it was trying to reuse the circuitry, you tried to get rid of the circuitry.
You'll have
How
probably
does it all
diminished,
work out?
yeah, you'll probably actually have less gains in the fracturable LUTs, so when you combine both, right?
I
Say a
would
6
guess
LUT,
that,
if
but
you
the-
had 2 5 LUTs inside versus now you have a 5 4 LUT, you kind of reduce the amount of unused circuitry, right? So, yeah, I'd be with you, I guess that, yeah, you probably have less gains from fracturable LUTs. The gains might add up to more than just fracturable LUTs alone, though I don't know, yeah.
Yeah, so I think it's interesting, because I think there will be an interplay there.
Sure, yeah.